Yeah, thanks for the nice introduction. So I'm Kavi. I'm an engineer at Grafana Labs. I live in Netherlands. I write a lot of Go for living. I'm also a Rust fan, like everyone here, I believe, particularly Rust type system. So today it's about building our own ARC. ARC stands for Atomic Reference Counting. It's a chapter 6 from this amazing book, Atomics and Logs by Marabos. So yeah, let's get started. So this is agenda today. And before that, on the right side, you see my copy of a book signed by Marabos herself. So yeah, that's she also lives in Netherlands, by the way. So I met her in another meetup. And yeah, she signed the copy. So today agenda is so we first understand, we set some stage to understand why we need some data type like ARC, right? And then we go through what are the API when we say we mean using ARC, right? What are the expectations? What are the methods? What are the functions we want to build or use ARC if you want to? And then we'll focus on some of the building blocks, kind of like a quick refresher of some of the concepts and the topics which we needed to build ARC, which was in the previous chapters. So that's one of the thing with this book. So it's a great book. Like it's hard to read, at least for me, every single chapter separately, because it needs a lot of context and ideas from previous chapters. So we just quickly do some refresh there, and then finally, yeah, we build our own ARC type. That's the goal. So why ARC, right? So this is a definition from Rust standard library for ARC. So ARC T basically gives you shared ownership for the value type T allocated in a heap. And this is also means like this shared ownership is being managed by having a reference count, which is atomic, meaning that this ARC type is safe to share and it's thread safe, basically. So in practice, this is how it looks like. You can have some data living in a heap, in this case, just data 3, right? And you can share the data among multiple threads and have access to it, basically. So that's what we're doing here. So you create something on the heap and then via ARC, and then you just create a clone of it and then send it to different threads, right? The thing to note here is the move keyword here. So what this means is you're basically transferring the ownership itself. What that means is whoever the owner, whoever the thread that takes the ownership is now responsible to handle the deallocation, like calling the drop method on the cloned object, basically, right? So, and as soon as, I mean, I'm also like a Rust beginner. I never have much experience with Rust. So whenever I hear like sharing between multiple threads, my mind automatically goes to something like this, right? So instead of ARC, can we have still an object at a heap and then create a shared reference and then use it in multiple thread, just like the example you see on the left, right? By the way, this is a working code, should be fine. And this gives like the same output like the previous one. So yeah, we're just creating an object on heap, and then we're creating a shared reference, and then we are passing to multiple threads, right? The difference here is there is no ownership transfer here. So meaning still there is a single owner, like A, for example, and that is solely responsible to clean up the resource by calling the drop method, by deallocating it when we are done with this object, basically. So, and the other thing is here we need to, even though it's not fully visible, like the variable B has a lifetime, right? So every time you create a new shared reference, you have to deal with the lifetimes, which may not be, which may not look that painful here. But if you look at the example like this, the one on the left uses ARC, whereas the one on the right uses a shared reference. So as soon as you put a kind of like a shared reference in the struct, then there is a bit of a chaos, right? So then where does this reference comes from? What lifetime it has? Then you need to include the lifetime parameter in your struct. And yeah, you need to manage this lifetime every time you instantiate or deal within multiple threads, right? which is kind of like a bit annoying. So the arc is useful here because you don't have to worry about lifetime. You can treat it as a owner, because every thread who has this cloned object can still call drop method as if it's the owner. So yeah, that's what I want to make it clear, because I had this questions as when I start reading about arc, when I start using arc, how is it different from shared reference? So the important thing to note here is arc is completely shared ownership. It has nothing to do with a shared reference, for example. So that's the main difference between arc and shared reference. So before building the arc type by ourselves, let's see what are the expectation of arc type, right? What are its API? So don't worry too much about the weak type on the right side. We'll get there, and we'll understand what's the rationale for having such type. So looking into the API, so we have this arc new. That's how we create a arc object. And the next three, clone, deref, and drop, are basically we are implementing some tries, right? Clone try, deref try, drop try. So note we don't implement deref mute, meaning like we don't unconditionally provide the exclusive reference to our data in the arc. And we'll learn why is that soon. And even though we don't provide a unconditional dereference mute, we provide a function called get mute. So note this is not a method, this is just a function which takes another arc object. And we make sure whenever we give out the exclusive reference, there is only one arc exclusive reference available throughout your application, basically. So weak is something you need to break a cycle, which is one of the problem with a basic arc we'll build later. So what that means is if you have like a two arc object pointing to each other, then you cannot drop the actual allocation because you'll have at least one active reference all the time. So in order to solve the problem, we have weak, we introduce weak. The standard library weak has a function to create a weak object like weak new, but the book, the implementation we're going to do doesn't have any weak. So the only way you can create a weak pointer is by creating an arc and then downgrading it to a weak. And only way you can use the value inside the weak is by upgrading it back to arc. So yeah, so basically like you have some weak reference, and if you want to access the whatever the type inside, you just call upgrade on it, and then it will give you the option of arc. So if there is no t, let's say the t is deallocated or like dropped, for example, then you will get a none, so you cannot use the value. That's the idea. That's kind of like a API we are talking about when we build arc. So like I said, like this chapter, at least personally me, it's hard to read as an individual chapter. You need some kind of previous knowledge. So that's what we're going to do quickly. The first thing is thread safety, right? So since arc, by definition, we are dealing with multiple threads. We have something like a some heap owned data we are sharing with multiple threads. So we need a thread safety, of course. And in Rust, the thread safety is done by two threads, send and sync. And both are auto threads, meaning usually you don't have to worry about those threads. It will be implemented for you. For example, if you have your own type, and if like a struct, for example, and if all the fields inside that struct is send and sync, then your struct is already send and sync. But what exactly is send and sync? So when you say the type is send, meaning it can be, the ownership can be transferred to the another thread, right? So what that means is like you create an object in one thread and you can transfer the ownership to the other thread. So from that point on, it's up to the other thread responsibility to call the drop and to deallocate the resources, so on and so forth. So yeah, so for example, like arc, of course, has to be sent, but whereas it's a single thread version, which is RC, like a reference counting one, it's not a send. So if you try to send RC between multiple threads, the compiler will be unhappy, saying it's not sent, basically. So also one thing I learned like 2 days back is the mutex guard, which you get by locking the data if you use mutex, is also not send. So the reason being, like whatever the thread that created this mutex, how to drop that mutex code because of some OS restrictions. So yeah, that's something I learned 2 days back. And for the sync, so sync is basically like there's no ownership here. It's just like if you want your type to be shared, like to be accessed from multiple threads, so it has to be sync. Usually, like a lot of copy types are sync. Like you can just share freely. The thing to note here is, for example, the cell, which is not a sync, but it's a send basically. So you can create a cell in one thread and then send it to other one. The other thread will take care of cleaning it up, but you cannot share the single cell with the multiple threads. The reason being, like the internal mutability of the cell is done without any synchronization methods. So it's unsafe basically. So why all this matters? Because we need to implement these traits for argt that we're going to build. And one subtle and the tricky thing is, whenever we build, whenever we implement these traits for argt, there is a boundary check. The T has to be both send and sync. So we will learn why is that in a few minutes. But yeah, that's something to think about. It's a bit tricky to understand, at least in my opinion. So the next building blocks is atomics. So atomic operations are like they are like a very basic operations you can perform on a data, and which is either done or not happened yet. So you cannot have an intermediate state. And atomic operations are literally the building blocks of anything that deals with multiple threads. So any abstraction like mutex, condition variable, even arc, so we're going to build that that needs to work with multiple threads. That is some atomic operation somewhere. And atomic operations are nothing but methods on atomic data types, like atomic I32 or usize. And so these atomic types, they can be like mutated with a shared reference, because for the same reason, like whatever the mutation you do, it's either happened completely or doesn't happen yet. There cannot be like an intermediate state. So it's safe to do via shared reference. Also, one thing worth noting here is the atomic operations are, for example, like there is atomic usize and there is the usize, the normal usize. So whatever the memory operation you do on atomic usize is relatively expensive compared to the normal usize. And why this matters? Because when building our arc, we use this atomic usize, like multiple atomic data types. And at the end, we optimize to reduce the number of atomic operations we make because it's expensive overall. Some of the atomic operations we do in building our arc is like a basic store and load, fetch, add, fetch, sub, and compare, exchange. Just a quick refresher there. And the final building blocks is memory ordering. So memory ordering is, so if you want to know, dig deep, there is also like a video in the recorded previously. But the bottom line is, like, when you have multiple atomic operations going on with multiple atomic data types across multiple threads, by default, there is no guarantee what order these operations are happening from different threads point of view, right? Usually it doesn't matter, but when you want to do something across threads that you want to that you want to guarantee, like some operations happen before some other operations in multiple threads, then we need to be expressive about the memory ordering, which operations. Basically it's a way to tell the compiler and the processor how to order the atomic instructions that deals with multiple threads. And formally, we define this ordering via happens before relationship. So quick example here is, we have different memory ordering, and I'm gonna just touch on this release and acquire. That's the one we use for arc. So we use this two memory ordering, release and acquire, as a pair. So what that means is, like, the acquire is used for load and the release is used for store. So when they use in pair, you can always guarantee that acquire load always happens after the release store. So whatever the value stored with the release memory ordering will be observed by the acquire load. That's kind of like a basic idea to establish this happens before relationship. So in this example, we have two thread. the spawned thread is basically like storing something in a data and storing some value in the ready state, whereas the main thread, which is spinning and try to load via acquire memory ordering whatever stored in ready state. And because we are using this release and acquire, we can guarantee that whatever everything that the store happened on ready state will always be seen by the load acquire in the main thread, the while loop. So that's how we establish that happens before relationship. And the final one is fence, and we also use fence in Arc. So fence is basically like you are separating the memory ordering from the atomic operations, right? So every atomic operation needs this argument to pass the memory ordering. So fence is kind of like decouple these two things. Why? Two cases. One, if you want to combine the memory ordering for multiple atomic operations, instead of like giving every single operation. So you can treat everything as you can pass relaxed, which is like a least expensive one. And then you can put a fence so that you can combine the memory ordering of multiple atomic operations. So meaning like you can establish happens before across multiple operations in different threads. That's one use case. The other use case, which is important, which also what we use in Arc, is conditional ordering, right? So if the example on the left is basically you are doing acquire loading, irrespective of whether P is null or non-null, non-null, right? So the compiler, the code generated by the compiler will make sure it always does the acquire load on the left side. Whereas on the right side, it does the relaxed loading every other time, and it uses acquire loading only if it is non-null. And that's the code generated by the compiler telling what to do. Don't do it in this order, basically. And we use this in Arc and the conditional ordering. So that's something to keep in mind. And that's about the refresher. Now we'll build our own Arc, right? So what's the idea here? What are we actually trying to do with the Arc? So like we saw before, the expectation here is whenever you put some data type in Arc, and that data lies in a heap, right? And every time you clone it, you don't allocate any new data. You just share the same data which is already in a heap. It's similar to box in a way, but calling the clone will not create a new allocation. It just shares the same allocation. And we provide API, like a safe API on top of it, how to do this very efficiently and correctly, which is important across multiple threads. That's the goal. So we have 3 different versions of Arc we'll build. First, we start simple, and we gradually add feature and optimize it. So the first thing is basically the simplest one, right? So the basic reference counting. So we have this. So this is what it looks like. We have this thing called Arc data. So Arc data is something which is what will be in the heap, right? So yeah, it has reference count and the actual data. And based on how many, and whenever we create Arc, this is what we basically giving out to the client, like to the user. So this is like that is a pointer to this Arc data, and every time we clone it, we just give out this pointer out there. And so the Arc data itself is private, so we don't expose it outside world, whereas the Arc structure itself is public, so which has a pointer to this Arc data. So one thing to note here is like we need a pointer, right? We need some pointer to the Arc data. So usually how we do is we create some kind of box pointer to whatever the data, in this case Arc data, but we don't do that. Why? Because whenever you create something with a box, you have kind of like exclusive ownership, right? And that ownership is gone as soon as that variable or whatever the owner is gone out of scope, and it will be released, like will be deallocated automatically, which we don't want to happen here, because we want to have this we want to manage this ownership manually, so that we know when we need to decide when to deallocate that data from the heap, not automatically, but manually whenever we want to. And that's why we use this non-null type instead of box to store this pointer. And it comes with a cost, right? So back to the thread safety here. So since non-null deals with like a pointers without any ownership, automatic ownership, it's not like it doesn't implement send or sync trait, which is it's not safe to pass across different threads. So we need to implement it ourselves manually by unsafe code, which is telling the compiler, okay, we know what we're doing, just allow us to pass this type between different threads. And yeah, this is the interesting part where we set the boundaries for type has to be send and sync, right? So for both the traits, so doesn't matter whether the arc itself is send or sync. In both the cases, we want the type T, whatever we store in arc, has to be send and sync both. The reason being, think of it, right? So at any point in time, there can be multiple threads accessing this type T, and it is completely possible you create this T, like basically allocate this T in heap in one thread, and it has to be deallocated in another thread when the count drops 0, for example, right? So there has to be like a thread ownership transfer. So that's why we need to have a send for this type T. And why sync? Because we also give out the shared reference of T, because that's why we implement the deref trait, right? So at any point in time, there can be multiple threads having this access to like a shared access to this underlying type T. So that's why we need both send and sync boundaries for this type T, whatever you put in arc. So this is a constructor, like this is how we instantiate arc. So there are a lot of interesting things happening here. So one is, how do we create a heap allocated data that is completely not owned by anyone, right? So we do this by creating via box. So box will create a new allocation, and then we leak the data, meaning that data in heap no longer being owned by this box which created it, right? So unless someone manually drop it or deallocate it, this data will lie forever, and that's what we want. And then we convert that pointer, like we convert that heap allocated data into a pointer via non-null from, and then and then we store it in arc pointer basically. And also one thing is, like, we also have this helper function called data, which converts this non-null pointer to shared reference of arc data. The reason being, like, it's a helper function because we use this arc data shared reference in a lot of places, in dereference implementation, in drop, or in clone. Not clone, maybe drop, I guess. But yeah, we also use it in deref. So yeah, it's a nice helper to have. And this is private, by the way. No user can access this data with the API, public API. Next is a deref. Yeah, this is to, so whenever you have an instance of RT, you should be able to access T transparently. And yeah, we just implement this one. And note, we just call this private data function here, and just return this dot data, which is shared reference to the type itself. So this all looks good. The interesting thing is clone here, right? So this is one of the important API of the arc. So the goal here is, whenever we clone RT, we don't allocate anything new. We just increment this reference counter, hey, saying like, okay, there is now one more user for this data which is in heap, and we increment that counter, and then we share the same pointer, the self dot pointer, which is basically arc data on a heap, right? The thing here is what memory ordering to use here. So it's okay to just use relaxed, meaning, let's say there are like 10 different threads coming and cloning the arc, right? So it's fine as long as, because as long as we have a total count of 10, we don't care the ordering of this atomic operation. So which will happen, right? So if the 10 threads clones it, like there will be like a 10, the reference count will be incremented by 10. And there is one problem though. Since we use this atomic U size, which also has a maximum limit, right? Which is U size. It can be like 64-bit in a 64-bit machine. So this can overflow at some edge cases, right? So you can easily reproduce this overflow with this std mem forget, which just creates this clone, and then you can easily overflow just by calling this in a loop, for example. So how do we avoid this overflow? So we take a simple step. We just abort it, right? So whenever we think we cloned more than this U size max by 2 times, then we just abort the process. So I mean, whenever we have these many threads so then there is like a much bigger problem. So we just abort the process itself. So note here, we don't use U size max -1 because whenever we are aborting the process, it can also still take some time. And meanwhile, someone can still call clone and increment the count, right? So if that overflows, then the count becomes 0 again, and we don't want to happen, right? So that's why we have U size max by 2 on the safer side. And that's the step we take to avoid the overflow in our example. And then drop, which is also another important thing, right? So how do we, so this is when we talk about thread safety, this is one of the things where multiple thread can do to the arc type, whatever the clone you pass to them, because they are the owner, they want to call this drop method as soon as they are done with it in any thread. And calling the drop shouldn't deallocate the actual data. It should only decrement the count, the atomic count, right? And when it reaches 0, for example, no other arc references out there, then we deallocate the actual heap data. And that's what we're doing here. So there is one subtlety here, though. What memory order do we use here? So let's think about that for a while. So if we use relaxed ordering, then let's say there are multiple threads. They're trying to drop it or trying to done with this arc clone. So that can be the case if we don't have any memory ordering, then this can happen in any order, right? So there is a chance where one of the thread the data is already decremented because the count is 0, but that change has been not observed by some other thread, and they can still access the data. So there can be a chance where if we don't have any memory ordering here, if we don't maintain any memory ordering here, there can be a chance where the data can be accessed even after deallocating it from different thread, which we don't want to happen, which is undefined behavior, right? So the way we avoid is by having the happens before relationship here. So via this release and acquire memory ordering. So what's happening here is we want to make sure, so we don't care about the drop, no matter how many times called, unless it's a last drop method, right? Because the last drop method has to be called before, every other drop method has to be called before the last one. Because that way we can avoid this deallocation and accessing after deallocation. So also that's what this release and acquire does here. Another thing is we use fence here. This is for the optimization purpose. So like I said, we don't need this happens before ordering for every other times, right? Only we need it for the last drop. So every other time, it's just a simple relaxed one whenever we load it, but it does acquire load only at the final time, final drop via these fences. We have a basic reference counting ready, and it's time to test it. So in order to test it, so what's the goal here, right? Let's take a step back and understand what's the expectation of arc here. So we have some data that is in heap, and it has to be deallocated only once. And when everyone is done with it, every other arc clone is done with it, and it shouldn't be dropped even any one of the arc clone is alive, right? So for that, we build this type called deduct drops, which has its own drop method. And whenever this drop is called, we increment this num drop static variable to track whether this particular data structure, like data detect drops, has been really dropped. Yeah. So the expectation here is when we put this detect drops in arc type and we clone multiple times, doesn't matter how many times. So when every arc clone goes out of the scope, only then this drop should be called. So by end of the test, we should have only value 1 in number of drops, which means it's fine, it has dropped properly. And if the value is still 0, meaning there is some problem in our arc implementation, which is not actually dropping the heap allocated data, meaning like memory leak, right? We don't want to happen that. That's what we're going to test here. So yeah, it's a big test. I couldn't fit it in a single slide. So this is like a setup one. We create this type, and then we go from left here. So we create 2 arc reference here, and one of them we just send it to another thread. So now the ownership is being moved there, right? So as soon as the thread is done, the X is done here basically. So the arc clone X, its drop method should be called. But still, it shouldn't actually drop the detect drops because still there is Y, right? There is another reference to this arc. So that's what we do this asserting here. So it should be accessible via Y. And yeah, and then on the right, after the thread is done, now the X is gone, right? And still the original data shouldn't be dropped. So only after dropping the Y, also, we should see the actual detect drop has been dropped. And that's what we test finally. So the X will be done when we join the thread, and Y will be done when we call drop Y. And only then we make sure the actual heap allocated detect drop is being actually dropped by asserting it to count 1. So yeah, this should be working fine. Does it mean our arc is completely correct and safe? Maybe, or maybe not. So since every time we deal with multiple threads, right, things can happen, breaks and edge cases at weird point in time. So one of the things which author recommends for more testing and these kind of abstraction like arc, which has some unsafe code, right, is this tool called MIDI. So this is kind of like an interpreter which runs your Rust code, and it checks whether all the memory ordering and in your unsafe code is being done correctly, right? So yeah, there is also experimental support for detecting data races, and data races actually been detected by happens-before relationship, right? So if I think this is what the Go race director is also using it, if I remember correctly. So yeah, so I played with this example a little bit, and it it has so much more, and also there is this GitHub page which shows number of bugs it's actually detected in a real Rust standard library in the some of the Rust crates, and they publish all the findings there. It's interesting to check. So yeah, and give it a try. So yeah, so there is one thing missing with our basic reference counting, which is giving mutable reference, right, to the users. So still all the basic Rust safety still holds, right? Because the basic Rust safety is, as long as you have multiple alias to any single object, you cannot have exclusive access to it, right? So that's what we are trying to do here also via this get mute. And the thing to note here, it's not a method, meaning you can't call arc.getMute or something with any of the arc clone. It has to pass the exclusive reference of arc itself. So it takes an argument which is arc, which is exclusive reference of arc itself. So before giving out the exclusive access, we make sure this is the only arc clone out there, so that this will have exclusive access to the underlying type T also. And if we don't have such only, yeah, we do this check by the reference count, right? So if the reference count is not like 1, then there is no point of giving the exclusive reference. So we just return none in that case. And the thing to note here is we are returning a reference, right? So whenever we deal with reference, there comes a lifetime. So the tricky thing, which is not too obvious, is the lifetime of the reference we return of the type T also comes from the lifetime of the argument. So as long as the exclusive reference of arc itself live, we can use this mutable reference to the T itself, and it expires when the arc exclusive reference expires, which makes sense, which also still holds the basic rest safety, right? Yeah. So okay, so that's our basic reference counting. Are we done? Does that solve all the problems we have? More or less, but it has one critical problem though, which is using this basic reference counting, you can create a cycle. So what I mean by that is, for example, the code you see on the left, you have a struct owner, which has a list of books. Any owner can have multiple books. And it which is a vector of arc of book, because single book can be part of multiple owners, right? And the book can also have an owner, right? So what this creates, as you see in the diagram on the right, is, so you have like a two object, like owner and the book on the heap, and owner, and one of the field in owner, which is books, which reference the book object on the heap, and the book struct and the book data itself has a owner, which can refer to one of the owner object itself. So as you can see, this creates kind of like a cycle. So we have seen in the drop method, right? So the actual heap allocated data will only be freed if the reference count becomes 0. And with this example, this count will never be 0, because there will always be like a one reference existing to this heap allocated data, which means so even though you call drop multiple times, your data, the heap data lies there as it is. And it keeps growing if it's a long running process, and you basically have a memory leak, right? The good example here is also, like, you can imagine a tree structure where you have a parent and a child. So each parent have a pointers to a child, whereas the child also have a pointer to the parent back. So when you try to drop parent, it cannot do, because child has a parent reference and parent has a child reference. It's a cycle. So how do we solve this problem, right? So what did I miss? Yeah, I think this is just what I explained, memory leak. So I mean, to be fair, this exact example, using this exact example, you cannot create a cycle, because arc is like, it won't allow you to mutate, right? Like we saw before. So you need some kind of mutex or rewrite lock to create this cycle. I didn't include that because I don't want to complicate the example here. But what you can do is, instead of you can have like a mutex of arc in both the places, and you can mutate it in multiple threads, and you can create a cycle. And if you create a cycle and run the same test we did before, you will see the final assert is failure, because no one is actually dropping the heap allocated data. It's an interesting exercise to do. So what's the solution here, right? So that's where this weak pointer comes in. So weak pointer is more or less same like arc, but it doesn't prevent from dropping the underlying type T, right? So what this means is, you can have a single heap allocated type, like some object T, pointed by multiple arcs and multiple weak pointers. But as soon as all the arc reference is done, the T will be gone, will be dropped from the heap. It doesn't matter whether any of the weak pointer has reference to T. It may sound scary, like how come there can be some pointers out there without any data in the heap. We'll get there. So there is some safe API we do to avoid accessing this T via weak pointers. But we need to break this cycle, and it can be done. It can only be done by these weak pointers. So the bottom line is, like, whenever you have a weak pointer reference, it can also mean the T is already been dropped from the heap. So yeah, just something to keep in mind. So to do the same example like we did before, right? So the only difference is here, instead of arc, we use weak pointer here to reference back the owner. So what this means is whenever the owner is dropped, it doesn't matter whether any of the book has any active reference to the owner itself, because it's a weak pointer. We don't care. We just still drop the data. So there cannot be a memory leak. We still remove this data, remove this owner object from the heap, irrespective of whether any weak pointer pointing to that owner. Yeah, so we don't have a cycle if we use weak here. This is yeah, so how do we build this now, right? So if you compare it to our previous version, like a basic reference counting, we have one atomic counter to count all the arc reference out there. Now we have two, right? So that's the basic idea when you want to integrate this weak type. So the first count, which is data ref count, is still the same like before. It just tells you how much total number of arc clones are out there. And this data, we can confidently say, we can confidently drop or deallocate the actual data when this counter is 0, data ref count, right? And there is another count which we introduce now is alloc ref count, which basically is a combination of how much total number of arc and weak exists out there. And in other words, you can say this alloc ref count just keep track of number of arc data that is been live, not the T itself, just the arc data of T, right? So also another thing to, yeah, I mean, if it's still confusing, I think you will understand more when we see all the API implementation. But something to keep in mind is like we have two reference count. One actually points to the actual T, and the other actually points to the arc data pointer itself. Yeah. So also the data, the type of the data field has been changed. So before it was just T, now it's unsafe option T. Why unsafe? Because now imagine, so when we introduce this weak pointer, the thing matters now is there can exist arc data, this struct, with there is no data, right? The data can be freed. So whenever this happens, we need to mutate this data field and change this option type to none. And we do this via interior mutability, right? And because we only have this reference to arc data itself all the time. So that's why we need this unsafe cell to do this interior mutability to update this data to none whenever it makes sense. And yeah, option for the same reason, we need to differentiate between whether the T is being actually deallocated and dropped or it's still out there. And that's why we have option. So yeah, now if you think about it, right? So weak is something which keeps this arc data live. So also note here, like just because arc data is a valid pointer on the heap doesn't mean the arc data itself points to the valid T, right? The T would have been like dropped. We don't care whenever we deal with the weak. So, but weak makes sure, because once we gives out weak out to the clients, so we need to make sure the arc data is still there, right? So if you think about it, like arc now is just a superset of weak, right? So arc does everything like a weak does, plus it needs to make sure the T itself is live until the last of the arc clone drops, right? That's the only additional thing the arc does other than the weak pointer. So it makes sense to build arc on top of weak, basically, so that we have all this implementation only once on the weak API, weak pointer API, and then we add some extra things on the arc itself. So that's the idea here. Yeah, everything else, like we implement again this trait sync and send like before, but we don't do it for arc now. We just do it only for the weak, basically, because yeah, if weak has send and sync, then the arc is automatically send and sync, because that's the only field arc has. Yeah, the initialization, when we create a new arc, note this is like when you're creating arc.new, and it's same as before, except like we have two reference count now, and instead of using building the data, we just use a ref cell, we just wrap it, or the refs unsafe cell with the sum of data, right? Yeah, the data is same, except this is a private for week now, not the arc. And it's unsafe because we are actually like the self dot pointer is basically like arc data, a raw pointer, right? So yeah, we just have to convert into a valid reference. We have to do it by unsafe. Deref, and also note here, we are not implementing deref for the week. We are implementing deref only for the arc. Why? Because week, we cannot, so whenever we have a week pointer for the client, it doesn't guarantee that the T exists, right? So we cannot unconditionally give out to access shared reference of T for the week pointer. We can only do it via arc. We have to do it only via arc. Yeah, unsafe is there for the same reason. We need to convert the raw pointer to a valid reference for the T. Yes, so the clone thing, right? How do we create this clone for week and RT? So if you remember that the whole point of having two atomic counter is to track this week pointer also, right? So whenever you clone a week, you just have to increment the week pointer, the week pointer counters. Whereas we do for the arc, we need to do both. And because every time you clone arc, we need to increment the data reference count, which is how many data reference count of the T itself, right? And we, yeah, so by cloning week.clone, we are indirectly also incrementing the other count, because whenever you create a new clone for arc, we need to increment both the counters. This is something to remember, right? Because we'll optimize it later. So now every clone of arc touches two atomic counters. You need to increment two counters. Yeah, everything else remains the same overflow check, and we abort if anything happens. Yeah, the other crucial thing is a drop, right? How does the drop trait look for week and arc? So first, for the week, so when we drop week, we just only decrement the week pointer count, which points to the arc data, not the data T, right? And when we have only when no longer we have any week reference, then only we can deallocate this arc data itself, right? So it may be a bit confusing, like there is arc data pointer and there is this T itself, the actual data itself. So week pointers exist means there is a valid pointer to arc data, whereas the arc clone exists as long as the pointer to T itself exists. So this alloc ref count is, if you remember, is a combination of both arc and the week reference. So when this count is 0, what this actually means is, yeah, I mean, there is no arc out there and there is no week out there. So we can safely deallocate the arc data itself. So note here the self dot pointer, which here it means the arc data point itself. And we just create a box from that pointer, and then we just drop it, and which basically deallocates the heap allocation. And yeah, everything else also remains here with the fence and the memory ordering here, exactly like before. No change in there. And then this is for arc, right? So when we talk about when we reduce this week, we said like there can be the week pointer can exist without the actual data, right? So when we drop arc, we just we care about number of data reference count here, right? So this count, data ref count, only represents number of arcs out there. So as soon as there is no other arc out there, we can just deallocate the actual T, the actual data itself. And we do that by getting the pointer to the data. Note this is not an arc data. Even it's confusing. I don't know how I can, yeah, I think so. Yeah, so this is like a data T, not the arc data itself. So we get the data, the pointer to the data, and then we just so this is basically like when we have this unsafe cell of option, right? And we are setting that option to none. Basically, the actual T you put into arc no longer exists. It's been deallocated. There can be weak pointer though still out there. And whenever you want to use the weak pointer, whenever you want to use the data into the weak pointer, obviously you need to call the upgrade method, which checks whether the data is none and then return none, basically. And then this is get mute, right? So the goal of get mute here is to have the exclusive reference to the underlying T. And now we have to check, we have to make sure there is only one arc pointer out there and no weak pointer here, right? So before giving out the exclusive reference to the T. And that's what we do by checking the alloc ref count, which is combination of both arc and weak. And if that count is 1, we mean there is only one arc exists out there, and it is safe to give the mutable reference to the T itself. And if that's not the case, we just return none. And yeah, you cannot have a exclusive access. And in terms of lifetime, everything remains the same. The returned mutable reference, like exclusive reference to T, is valid as long as the lifetime of the argument of the arc itself. Yeah, no change in there. So yeah, we have this upgrade here. So this upgrade is basically how, so you have a weak pointer and you need to use the T inside the weak pointer. So how do you use it? So this is a case where even though you have a weak pointer, the underlying T could have been dropped because there was no arc, right? So that's what we do a check here. So we make sure the actual data ref count, which is the valid pointer to the actual data, is still there. If it's 0, then we just return none. So no, you cannot use the data because the data has been freed because there is no arc pointer out there. And if you still have at least one arc reference, meaning like we have some data that we can give out, right? Then yeah, we just basically return the arc of that data itself. We just clone the arc data pointer and then give it to the client. So now they can use the T via the weak pointers. We still have this assertion for the overflow. But yeah, the thing to note here is we don't need any memory ordering here because we don't have to make sure any other atomic operations has to happen before this compare exchange, basically, which increments this data ref counter, right? So we are giving out the arc, so the data counter has to be incremented, and we do that via compare exchange with a relaxed memory ordering. There's something here. Yes, so downgrade is simple. So downgrade is basically you have arc, but you need to have a weak pointer. And also, yeah, it's worth noting, like this is the only way you can build a weak pointer with our API. The standard library has weak.new, you can create weak pointers, but with our example in the book, you can create a weak pointer only by creating arc first, and then downgrading to weak. And whenever we downgrade to weak, we just increment only the ref count, which will be done by weak.clone, right? And yeah, we don't have to touch the other data ref count because we can give out weak as long as the valid pointer to arc data itself is present. We don't care about is there any valid reference to T itself is exists. T would have been like deallocated, doesn't matter, but still we give out the weak pointer. That's the whole idea. Yeah, so we are done with another version which supports the weak pointers where you cannot create cycle. So this is the same setup test we use for testing our basic reference counting. So we still have this detect drop struct with a custom drop method, which keeps track of how many times this drop is called, meaning whether this detect drop is actually being deallocated, right? So the same condition, the value should be 1 at the end of every threads or every variables goes out of scope of arc clone and weak clone, for example. So yeah, the actual data should have been dropped only once, meaning the num drop static variable should be 1. And if it's 0, meaning yeah, there is something wrong with our arc implementation, and yeah, it's not deallocated and memory is taken somehow. So yeah, it's a big test one. So we go from left to right. So what we're doing is we are creating a 1 arc and 2 weak pointers. So notice how we are creating a weak pointers here. We create an arc, then we downgrade it basically, right? For the same data, like hello string, the tuple of hello and detect drops. So yeah, I mean, maybe I should have mentioned before. So it's a tuple because the detect drop has a custom drop method. So whenever this data drops, the drop method will be called because it's a custom type and we can have custom drop method there. So similar to previous one, we just create a thread. We spawn a thread and we pass one of the instance, one of the weak pointer y to the thread, and we access and make sure the data is accessible via the weak pointer, which is true. And then meanwhile, we also access in the main thread via the actual arc pointer. So which should also be true because yeah, the data is not deallocated yet. Because the x still is in the x is basically arc here, right, which is still in scope. Yeah, so yeah, and we do the same thing here. We just make sure we can also access it via the another weak pointer via z. So we upgrade it and then try to make sure the data is still accessible, because only if the data is accessible we get otherwise we would have got none here when we upgrade it, right? So, and also we make sure the actual data is not released yet, like not deallocated yet. And finally, we drop the arc itself, drop x, right? So this drop x should decrement the number of arc pointers count, meaning it goes to 0 because we have only one now. And that should deallocate the actual object itself, the direct drops, and which is we are asserting here. And after deallocation, when you try to access the same data via weak pointers, by upgrading it, it should return none, because there is no way we should provide access to the underlying type T if it is deallocated, right? Even via weak pointers. So yeah, so just to clear it, like weak pointer can exist, which means there is a valid pointer to the arc data struct, but there is no valid pointer to the T itself, which has been dropped when we call drop x, when the arc count is 0. Yeah, so we reach the final version, which we'll implement. And why? So taking a step back here, right? This version we just implemented should work fine. It shouldn't have any cycle problem or anything. The only problem we have is like some optimization issues, right? I should not have put as a problem, just optimization. So there is no correctness problem or anything here with our previous implementation. So it just like, yeah, like I said, we introduced this 2 atomic counters, right? And every time you clone arc, you create a new clone of arc, you have to touch the 2 atomic counters, meaning like you are doing 2 atomic operations every time you clone arc, right? So the pattern here is like, yeah, I think people have arc much more often than the weak pointers. So why do you have to touch both counters when you're cloning the arc itself? Like, yeah, and also like a drop, right? Even whenever any arc clone goes out of the scope, which calls drop internally, has to touch 2 atomic operations because it has to update this total count, right? So yeah, the basic problem here is like, why do you have to, all the arc users has to pay for the weak pointers? And can we do something better, right? So just thinking of some potential solution, right? So if touching the 2 counters is a problem, can we treat both as separate pointers, so that whenever we do some operation, we do separately, right? Without any synchronization or yeah, treating completely as a 2 different counters. So there is a subtle bug there if we do that way, because that is a race, right? So so the following program, like function annoying, like basically it's creating, so it takes the arguments of some arc type, some valid arc type, and it just create a weak and then drop the arc, and then create an arc and then drop the weak. So basically it's kind of like switching between, at some point in time you will have, you won't have any arc references, and at some point in time you won't have any weak references. Meaning like if we treat these 2 counters as differently, then some thread which is running this annoying function can fool us, right? So we can still drop a data even though there can be some thread which has some valid arc references. So that's kind of like undefined behavior. So The conclusion is that we can't use this idea. We can't use this solution. So there is a better version though, which is a bit more subtle. And yeah, I have to be honest here. Like I never implemented this solution. I just read it in the book. The other two I just implemented. Yeah, I have like a much more understanding of from implementation point of view. But here the goal is clear, right? Like we explained before. So we need to optimize not to touch both the counters whenever we're dealing with arc. So the workaround here is to solve the problem is we still have two counters, but the second counter, which previously counted the combination of total arc plus total weak, which is why we need to touch every time we clone arc, right? Now that counter tracks all the arc references by incrementing only once. Like when we initialize this arc, arc.new, for example, that's the only time we put this second counter as 1 because we are giving out arc. And every other time we clone arc, we don't touch that counter. So now the cloning arc is very less expensive because you don't have to touch the other pointer. And yeah, so basically you don't have to touch the other counter unless you have like a final, like a last arc clone trying to drop it. Basically, that's where you need to check both the counters so that you can free this data itself. So the bonus optimization here is previously we are using this unsafe cell of the so the arc data itself, the pointer of arc data we store in either in the weak struct itself is done via oh sorry wait yeah, I think we are basically changing this. I think it's here. Yeah, I should have a slide here. So in the previous implementation, we used unsafe cell of option here. So instead of option, we use manually drop here. The reason is like it takes lesser space, and also we don't need option technically because the reason we use option there to know whether we have actually the data or we deallocated, right? And now we can know that just with a counter. So we don't need option there. So yeah, we have a manually drop here. So whenever we need to drop T from the heap, we just call manually drop or I think yeah, there was some method which I forgot, I guess. So to drop the T from the heap. Everything, yeah. So another important thing here is now to structure like arc and weak are completely separate. We don't implement arc in terms of weak like we did like in a previous implementation. Yeah, and everything else remains same. We need to implement this thread safety traits for both separately. And yeah, this is the idea, right? How are we going to make sure we don't touch this alloc ref count when we clone arc? And yeah, the idea here is no matter how many arcs out there, previously this count represent, let's say we have like a 4 weak pointers and 5 like a 4 arc pointers out there, we'll have 8 as a count here. So now it will be just 5 because all the arc references out there will be counted as just 1. And we do that 1 during initialization, like whenever we create a actual arc.new, and after that we don't touch it during a clone. That's the idea. So the new doesn't have any change here. As you can see, like this is when we allocate this alloc ref count as 1, that's the only time the arc is going to touch that counter. Yeah, so now we have this private function in both because now we have 2 different structure. Arc and weak are completely different now. Yeah, so the care should be taken not to implement dref for weak. Yeah, because we provide dref only for the arc, like transparently can reference a shared reference to the type T, not for the weak. Yeah, unsafe is for the same reason there. Yeah, mostly everything else remains the same. Yeah, like you see here, the private data is separate for week. And then clone is also doing the same exact thing, incrementing its own counter. So the clone here, so as you can see here, so yeah, the clone for the week remains exactly same like before. The clone for arc has changed because one of the main reason we do this is to optimize the clone functionality of arc. So note here, we just increment only this data ref count, right? Because the alloc ref count has already been put as 1, which is a share of this arc pointers, right? So, and we don't touch any of the counter here. Previous implementation, we used to clone that week.clone also, which increments other counter, but we don't have to do it anymore here. That's the optimization. And for the drop also, we just have to check only this data ref count. Unless there is yeah, so except when we want to doing the final drop here. So so think about this, right? So the share of ref count from the arc side is just 1, right? And we need to take that out. We need to decrement it by 1, because otherwise there is no way this weak pointers count will become 0. Because even though there is no arc reference exist out there, if we don't decrement this other counter in the drop method, this weak pointer counter will never become 0, meaning the arc data will never be freed when the final weak pointer is freed. Yeah, and that's the only case we decrement the other counter in the arc drop implementation. Yes, so I think we still have time, right? Yeah, not going. So I think we can still have like 3 more functions. I think we're done after that. So upgrade remains more or less the same. So only thing is like the previous implementation, because the arc is implemented in terms of week, we also clone the week, but we don't have to do this anymore, meaning we just also touch only 1 counter here. Yeah, everything else remains the same, like overflow check and compare exchange to increment the counter. This counter, the data ref count, is 0, meaning there is no T is there in the heap, would have been deallocated. So we just return none in that case. So yeah, so even though you have a weak pointer, you upgrade it, but you cannot use the underlying type T because it's been deallocated. Yeah, so the last 2 function is where it gets a bit tricky. I also don't have, I also didn't fully 100% understand, I think. But the idea is here is simple here, right? So at the high level, what we are trying to do here is, so get mute, the goal is to give a exclusive reference of the underlying type T, right? So we need to have some kind of memory ordering with a downgrade, which will be happening here, right? So the reason is like we and the way we have this ordering is by having some kind of synchronization between these 2 methods, having some kind of like a lock via compare exchange. So what we do here is we just the basic idea is like you can only give mutable like a exclusive reference only if both the counter is 1, right? So and since we have like 2 counters, we cannot check 2 counters separately because we miss this, that is inherent race between checking these 2 counters. So what we do is we just lock this 1 counter, which is alloc ref count, so that the downgrade function will not update it or something. And then we do this lock by putting some like a delimiter value, usize max, so that if anyone calling from a different thread, the downgrade function, it will do like some sprint lock. It wait for this to finish basically. Yeah, then so yeah, we give out the exclusive reference only if the count is 1, the both count is 1. So first we check the alloc ref count, and then we check the data ref count, and if both is 1, yeah, we just give out the reference here. the exclusive reference. Did I miss anything here? Yeah, I think the locking is the tricky part here. And on the other side, when someone else is calling the downgrade, at the same time the get mute is being called. So this will wait, the downgrade will wait via like spin loop. Yeah, so basically it also checks for the value which is given by this compare exchange. And yeah, and the downgrade is only success if if the count is basically like so where are we doing this count check here? Yeah, I don't know. I think I didn't fully understand this downgrade, I think. So, yeah, I don't know. So there was some memory ordering also happening here, which I also couldn't understand here. But yeah, if anyone can explain, it would be great. But that's our last API actually. And yeah, the win here is basically, yeah, I think author claims this implementation we did without touching like two counters every time we clone org. It's basically like similar to the one we have Rust standard library. So I didn't do any benchmarks or anything, and yeah, I don't know how the comparison is made, but that's the claim from the author itself. So I think we reached the end here. So the summary is RT provides a shared ownership, not the shared reference. Something to keep in mind. And yeah, we provide only the exclusive reference when there is only one org reference out there, because we can't have multiple alias and the exclusive reference at the same time as by Rust safety rules, right? And yeah, so the memory ordering is also matters here. So we can use relaxed memory ordering for everything except the final decrement, because we don't want to end up in a situation where we deallocate it, but then some other thread access the value on its undefined behavior. Then we introduced weak pointers, right, to avoid this problem of cycles. And we saw how it prevent building a cycle by having some weak pointer out there, even though the T is deallocated. So that breaks the cycle. And yeah, the non-null type represents, so this is the type we use to store the pointer to org data. So we always have the valid pointer to org data, and be done by this non-null type. And we used manual drop as optimization, so to save space. And yeah, and also if you remember, like a final version uses the manually dropping stuff option. And yeah, also the final optimized version we saw, when we want to optimize something that deals with multiple atomic variables, it gets a bit complicated. And yeah, sometimes it's easier to wait over some spin lock when we want to when we want some kind of ordering, or when we want to deal with multiple atomic variables in different threads in different methods. So that's what we did with the spin lock on the downgrade, whereas the get mute is locking this allocref count value. So that's it. That's all I got. So yeah, if you have any questions or discussions, feel free.
That was great, Kavi. Yeah, I speak for so that is it's quite a tough chapter to cover, even though it's quite implementation heavy, because there's a lot, like I say, there's a lot of concepts in there.
Yeah, it's basically putting together everything you read in past 3-4 chapters. Yeah.
Got some time for discussion now. Do anyone have any questions or things they want to call out? I mean, the downgrade bit at the end, I think I also need to reread that section and check my understanding on it.
Yeah, I think the goal was very clear why we are doing this one, but the implementation, I think, yeah, I'm in the same boat here. I think I need to implement and see, because the lot of learnings personally for me came from this chapter is by trying to do what they say not to do, right? They say don't use box. Okay, I will go and use box. What happens? So you learn something there. So, and they ask not the type should be send and sync. Okay, what if I send a type that is only sync? What happens there? So yeah, a lot of learnings comes in that way. Yeah, I didn't get a chance to implement the third one. I'm a bit, I didn't get a chance. Yeah, I also wanted to do the benchmark, but I didn't get a chance to do. If anyone else has any thoughts or something to clarify there, feel free.
I know we had some good chat in the chat about get mute, because it is a bit subtle even just in the normal case, figuring out why get mute is fine. And it does all check out. You're kind of leveraging kind of two pieces, which is that that you can rely on the atomic value being consistent across. If it's one, it's one. There is only one about, and if there's only one about, then if you have a mutable reference to an arc, it has to be that one. There can't be another one that getting cloned on another thread somewhere, because you have to have the only one. There's no way there could be another one on a different thread.
But what I missed was that when you create an arc and you pass it to a thread, at that point you can't clone it again because you passed it to a thread. So you've moved it in,
unless you've kept.
You need to clone you need to clone it twice before you pass it to the first thread, which means that by the time the thread gets it, the reference count is 2.
Well, one clone, but reference count 2, giving you 2 arcs, because arc new, and then the clone is the copy. But it amounts to the same thing. You need to have 2 arcs in order to be able to move one into another thread. And if you have 2 arcs, the count is 2.
So you can call get mute on another thread.
Yeah.
In which case you need to use a mutex inside the arc to get that mutability.
Exactly.
Yeah. So by default, like my understanding is there by default you have only the shared reference, not a mutable reference there, because so that's why this get mute accepts like a shared exclusive reference of the arc itself. So in practice, you can only have such exclusive reference either before sending it to a thread, like you are the only one in the main thread or something, or once all the thread is joined, and you can make sure there is only one reference of arc.
That's right. Yeah. So you get mute is not usable on a different thread.
Yeah.
Which threw me off a little bit, because quite often you use arcs on different threads, right? So why have a method at all where you can only use on the original thread you created it? But
well, you can use it on a different thread to the one you created it on, but you have to move it into the other thread. You can move it wherever you want, but there just can only be one at any point. At the point at which you call get mute, there is only one. You can call get mute when there's more than one, but if there is more than one, the next check fails. So then you don't end up getting it mutably anyway, and it returns a none.
But if you're creating an arc and you move into a different thread, that kind of defeats the purpose, unless you want that thread to create clones. But yeah.
Also, one thing which I find a bit hard to understand before is when I read this get mute. Okay, we are giving out the mutable reference, like exclusive reference, and they can do whatever they want with it. How do we get it back? Right, once we give out this mutable, so that's where this lifetime kind of comes in the play. So whenever you return the reference, it has the implicit lifetime, and the lifetime from the argument itself. So you don't have to worry about what they do with it, as long as that argument lifetime is valid. You return this valid, so it expires along with the arc mutual, the arc exclusive reference as well. So.
Actually, that part I was very comfortable with, funny enough. You can just scope it.
It's the borrow checker paying for itself again, isn't it? By making your ref t, the lifetime of your ref t tied to your ref self, it means that your the arc you called, you need to still have the you can't have the original mutable reference at the same time as your next one.
There's also an example of lifetime elision as well in that function.
Yeah.
The output parameter is the same lifetime as the input.
the downgrade on the last example, I definitely need to reread that section to understand why you need to check for usize max.
Is that to stop overflow?
No, this is the last optimization where you're using usize max as a special value. It's a bit different. It's quite different to the rest. It's like the final optimization, but it's just a bit.
I think before the implementation, specific implementation, never let the reference count go over max divided by 2. So
yeah, that's slightly separate. But I'm talking. So in the get mute method, or for the final optimization, there's this compare exchange where you swap a usize max in. That makes sense. I get that. So you basically can have that alloc ref count be usize max. So you've essentially locked alloc ref size. But then what I'm not clear on is then why downgrade needs to have a spin loop in it when n is usize max. I just need a second to probably sit with it a bit longer.
Yeah, I think I know why they're doing it, but I didn't fully understand the rationale behind it, because they're doing it because they're avoiding the alloc ref count to be changed by the downgrade function, because here's the idea, right? So in order for a get mute to be success, they have to make sure they have to check both the counters, alloc ref count and data ref count, to be 1, right? And when they do it separately, so there are one thread accessing get mute, one thread accessing downgrade, so they cannot do it as an individual check. So they have to lock one counter so that the downgrade doesn't change it, and then they have to check the data counter. So that locking is being done by this compare exchange by setting to the value usize max. On the other side, it has to wait till the value is usize max. So the downgrade won't change this counter till the get mute is done with it.
But couldn't you not call downgrade anyway? Because if the only way you can call downgrade is if you have an arc pointing at the same data, but you can't have an arc at the same time you can't have another arc at the same time you're calling get mute, which is the thing that sets in the usize max for the temporary lock. So that's where it's not quite straight in my head. I probably just need to read it again. But
I see what you mean. So this argument exclusive reference to arc, and the one who is calling the downgrade cannot exist as same time.
Exactly. So then why do we have to check it? But there must be a reason, but I'm missing it.
There's always a possibility that you're smarter than the author, Kiara.
That is definitely not the case. I am 100% sure. But
I thought I knew Rust, but you schooled me today.
I read the chapter really carefully. It's yeah.
That's what makes you a good programmer, due diligence.
Yeah, awesome chapter. Did anyone else have any thoughts or takeaways?
I think I need a holiday to recover from the first 6 chapters of this book.
Well, topical, right? I will share screen and move us on to just talking about what's coming up.
Good segue.
Yeah. Sorry. All right. So, if you missed any of the previous talks, they're all on YouTube. This one will go up soon. Sorry, I was so slow on the last one. I know I say that a lot. I will try and be better. But yeah, we've got lots of content online. Upcoming meetups. So we're going to have a short break from the book for a couple of reasons. One is that we've got 2 non-book club related talks coming up. One is still parallel, related. It'll be a good kind of refresher on some of the other things related to concurrency, not purely just atomics unlocked. And that's insights on concurrency. And then we've also got a speaker we've had before, Joshua Burrito, who's worked on Valoran, which is an open source Rust RPG, and it's a brilliant game, and he's a really, really nice guy and excellent Rust developer, and he's going to come do a talk for us on combinator APIs, which is something that he's quite keen on. And then we're going to have a break in August because of various vacations. People are away during summer quite often. We've got a few videos from previous meetups that we'll put out in August. but we will not have any in-person ones. The Discord will still be active. We can chat about the other upcoming stuff. And then we'll restart with the book club on 6th of September, just like a school year. Think of it as your summer holidays. And we'll kick off with chapter 7, which is definitely a chapter I would recommend reading before if you get a chance, because it's a bit different to the other ones, I would say. And it starts the second half of the book has slightly different sense to the first half of the book, and that's like the turning point one. So yeah, really looking forward to that. We've also it's not written on here, but we do have a speaker from Surreal DB who's going to do a talk for us in September as well. That is now
Nice.
confirmed. So I'll get as soon as I have like the exact content of the talk or like a vague description, I'll let you know. But we have the speaker. Yeah, and if anyone hasn't done a talk before in particular and would be interested in taking one of the later chapters, you know, we're always trying to get new people. Obviously, we'll also definitely have current speakers back, but if there's anyone who fancies it, I realize they're not the most approachable chapters necessarily, so they're maybe a bit nerve-wracking, but I'd say like this is quite a warm, welcoming environment, and you don't have to know all the answers. Definitely with a book like this, they're not expecting you to be an expert, so it just gives you a chance to read it in a bit more detail and process it a bit more, read around it. It's yeah, so if you are interested, then please drop myself or Chris or Alex or Matt a message, or just post in the Discord or anything, and then we'll get you queued up. But yeah, thank you again, Kavi, for the brilliant talk. That was great.